years being apart. So as most of you know, this workshop was planned to happen in 2020, and due to the pandemic, we had to postpone it. But now we're here, and it gives special flavor to have you all here. So I just want to say a few words to be very quickly to open and start the real thing. So first of all, little basic warnings for you to survive in São Paulo. You are not from here. It's very important. So don't trust this, okay? So wait for the car to stop for you to cross the roads, please. Don't drink tap water, and you'll be fine. So this workshop is sponsored by ICTP-SAIFR, by the Latin American Center of Physics, and the Young QCD initiative. So let me just say a few words about our primary sponsor, about ICTP-SAIFR. ICTP-SAIFR, so the workshop is mainly supported by ICTP-SAIFR. It's part of the 2022 activities of this institution. So this institution is a partner institution of the Trieste ICTP, that, of course, all of you know. It was the first partner of this type out of Italy. And it shares the physical space and resources with the Theoretical Physics Institute, which is part of the State University of São Paulo. So this building is, this small campus is part of the São Paulo State University. And ICTP is supported by private and public funding agencies, including, of course, Italy, ICTP, and FAPESP, and some other sponsors. And the idea is similar to what happens in Italy, and it promotes several events during the whole year. So there are schools, workshops, mini courses, and a lot of outreach activities. So there are outreach for a general audience here and outside here. So there are events in museums, bars, all kinds of places. Also for physics undergrads, many activities for high school, both students and teachers. So it's a very interesting and live place to be. Just to have an idea of the numbers, the ICTP started activities in 2012, and until 2019, I mean, before the pandemic, they had like 257 activities. Almost 2,000 visiting scientists had been here, and more than 5,000 students participated in the activities. That was before the pandemic, so since March 2020, it started to promote online activities. And during those 2 years, or almost 3 years, it was more than 50 online activities. And there is an open call for proposals. Anyone can propose activities. You need a partner from Latin America, but not only people from ICTP. So the call is now open for 2024 activities. If you want to check it out, it's in the ICTP webpage. So just a few announcements. Coffee break will be, for those who don't know here, coffee break will be in the mezzanine area upstairs. Those who will present posters, you can hang your posters there. There are supports for them. You can hang it today, or if you prefer on Thursday, but I think it's better to do it now because the people can take a look during the coffee break. Apart from the coffee break, there are coffee capsules. If you're a fan of fancy coffee, you can get real coffee in the secretary office, but then you have to pay for it. There are T-shirts and mugs of ICTP for saving the secretary. So if you want to bring something to remember our event, you can get it there. And we'll organize an informal dinner on Thursday. To be, we're choosing the place. It's not official, so those who want to participate, just go, pay, each one pay its part, and that's it. I will give you more details tomorrow. And that's it. I wish you a productive workshop, and let's start real physics. Thank you. The first speaker is William Tavares, so please, William. Você prefere esse microfone ou...
Tanto faz, acho que pode ser um microfone.
Pode ser um microfone?
Uhum.
Você subiu para esse
Tá
computador?
aqui, ó, esse arquivo aqui.
Para agora passar para o outro. Esse?
É esse aí. Não, esse não. Não é esse. Esse aqui, ó, main. Aí pra mudar aqui é só...
Como é que eu faço para esperar a apresentação?
Funciona?
Sí.
Ok. No, porque lo cambié de computadora.
Ah, sí.
Sí, sí.
Si solo no sabe cómo poner isso. No view no te dá nada?
View.
Viu? Tá isso.
No, pero si apretas en View,
Aí apertei.
no pasa nada.
Esse passa.
Ah, bueno, algo pasa. Pero
E como eu compro ele? Posso ler? Não. O que é esse todo?
Flip page option.
Destination.
Bueno, esa pues, si apretas
Sí,
ahí.
de repente se bota aquí, pero bueno, que é mais grande.
It's not
Yeah,
view.
pero ahí.
Bottom right.
Ok.
Só ir pra frente aqui.
Thanks.
Ok. Thank you. Can I start? Hello, everyone. Good morning. Today I will talk about the importance of some different regularization prescriptions in the context of the two-flavor and Nambu-Jonas-Vinho model. Of course, these procedures I will present here are applied to the extended versions of this model too. So, and as an example, we will use these methods to see the behavior of the effective quark masses and the meson masses in the NGL model. Here, I will try to convince you that the magnetic field independent regularization applied to the magnetized NGL model can avoid several non-physical results that usually appear when these methods are not applied in the NGL model, okay? And this presentation has these 5 points here. First, we will see some basics of the NGL model, and followed by the regularization procedures. We have 2 main procedures that we can study a little bit, and we can apply these methods to the effective quark masses and the neutral Hall meson. That is the main example I will show, okay? So we will see the results and some summary conclusions. First of all, it's interesting to try to understand why we are interested in magnetic fields in quantum chromodynamics. I think in this workshop we will see a lot of interesting news about this issue, so I will quickly review the 3 main points that we usually use to to study magnetic fields in quantum chromodynamics that are the non-central, the magnetic fields in non-central heavy ion collisions that appear in the perpendicular direction of the reaction plane. We also can have these strong magnetic fields in some types of neutron stars called magnetars, and we also can look to the primordial universe in electroweak phase transition, okay? We can look to the LATSI QCD and try to see what they tell us. In fact, they tell us a lot of things, but the main result that we're interested for this work is the magnetic catalysis, which is the enhancement of the chiron condensate as function of the magnetic field that we can see in the red line. This effect mainly occurs at 0 temperature. And we can also look to the inverse magnetic catalysis. We will not look to this problem here, but we can have this non-monotonic behavior of the chiron condensate as function of the magnetic field to temperatures close to the pseudo-critical temperature, okay? If we go to the basics of the NGL model, we can see that we have the Lagrangian equation 1, that we have basically this structure. We have the Dirac part that is coupled with the electromagnetic field through the covariant derivative. We also have the current quark masses in the isospin approximation, so we have the up and down quarks with the same mass. We also have 2 4-point interaction channels and a coupling constant that has dimension of inverse energy squared, which shows that we have a non-renormalizable theory. And we also have to choose a gauge in order to have a constant magnetic field in the z direction, okay? And in this work, we used a simple mean field approximation. So the mass term now is redefined by the equation here, right, in equation 2. So we have an effective quark mass that depends on the chiral condensate. And this equation is called gap equation. In order to obtain the full result to the effective quark masses, we have to evaluate the quark condensate. The quark condensate is the four moment integration of the trace of the quark propagator, but we are working in a magnetic field environment, so we have to use the quark propagator in a magnetic field, and for this purpose, we can use the Schwinger result for a fermion in a magnetic field. So when we take the trace in the color, flavor, and Dirac space, we can have these 2 main results here. This is not the only these 2 representations are basically the 2 most used one, but we can change the representation by simple trigonometrical transformations. In the first, we have the Schwinger formalism, in the second, the Landau level basis formalism, okay? These 2 equations are ultraviolet divergent, and we have to choose a way to regularize. In order to do that, we can use the first central procedure, that is the MFI procedure, magnetic field independent regularization. Here, just for a quick explanation, we can expand the hyperbolic function that we have in our integration in order to see what is the divergent contribution to our quark condensate. Here we see that the first term gives us a divergent contribution, so we can remove this contribution, okay, and we can also have to put the same contribution. But when we include this new contribution at the end of equation 6, we have to regulate with the usual regularization that we can choose for the vacuum regularization of this model. When we look more closely to equation 6, we can see that we have a pure magnetic field contribution and a vacuum contribution. So these dual contributions are now disentangled. We can do a little bit more of calculations and avoid the integration that appears in equation 6 for the pure magnetic contribution, and have our analytical result in equation 7 for this magnetic contribution. Of course, we have also some simple types of regularizations for this problem that are the non-MFI regularizations that entangles the magnetic field and the vacuum contributions in the same quantity. If we look for the first case in the proper time regularization, we can just put a cutoff in the lower limit of integration and end of story. Okay, here the contribution of magnetic field and vacuum are entangled, and I will show you that this can change the results for the quark condensate. We also can use the Landau level basis, and we can use some form factor function to regularize the quark condensate in the ultraviolet limit, and we can choose some form factor function in equation 8 and 9. Okay, usually this form factor functions can give us some new parameter, and the main idea here is the magnetic field and vacuum now are entangled in the same quantity. We can see here the difference between the application of these two methods to the quark condensate as function of the magnetic field. Of course, here we compare with some lattice data, but the idea is here at the first place that when we use the non-MFI procedure, we have this several oscillations that are usually also confused with some other physical quantities, okay? And when we use the MFI procedure, we have a more smooth result for the quark condensate as function of the magnetic field, okay? So once we have set the magnetic field independent regularization, we can look more closely to what we want to study. Here, for example, we start with the gap equation, equation 10. We have a pure vacuum contribution and a pure magnetic field contribution, equations 11 and 12, okay? And now we have chosen the Pauli-Vilas regularization for the vacuum contribution, okay? Here we have a high definition of the effective quark mass that depends on this new Pauli-Vilas coefficient that depends on the way we regularize the vacuum, but this is the main idea. We are interested here also in evaluate the meson masses. As an example, I present here some basics about the pion mass in the NGL model that we can do using the usual random phase approximation. In order to do that, we change the meson propagator for this infinite series of polarization functions of quark and anti-quark, okay? And we can look to the denominator of equation 13 and try to see the mass that appears in this propagator that's given in this numerical solution of equation 14, okay? But we have to evaluate the full trace in the direct flavor and color space equation 15 for this polarization function for the pion. Of course, for the NGL model, we also have the sigma meson mass to evaluate. If you want to include vector mesons, we have to put also 4-point interaction channels with vector interactions and a new coupling constant. Now we have in equation 18 also a polarization function for vector mesons, okay? If we work a little bit with this new polarization function, for the vector channel, we can look to a basic Schwinger-Dice equation for this problem, okay, that we can write for the vector mesons. And as we are interested in neutral vector mesons here, as a first approach, we can simplify the Schwinger-Dice equation, and we are interested in meson masses, so we can use the rest frame of reference. And also, if you look for some symmetry in our problems, we can see that the polarization functions with 1, 1, and 2, 2 are the same, and we have to evaluate just the polarization function with 3, 3 in order to full calculate the meson masses with different spin projections. We can see this a little bit more clear with decompose these polarization functions in some bases very an idea very close to that we can do to the photon propagator. So we can decompose the Schwinger-Dice equation and the vector meson polarization function in this basis. We can obtain the 3 Feynman propagators for 3 different spin polarizations that are plus, minus, 1, and 0. And we have to evaluate for symmetry just these 2 equations to obtain the vector mesons mass. Okay. We can start in the vacuum. It's a simple calculation. We can avoid a very general. We can obtain a very general result in equation 20 when we parameterize this effective quark mass depending on the Feynman parameter and the Pauli-Vilas coefficients. And if we evaluate this equation 20 in the limit of the rest frame of reference and using the Pauli-Vilas regularization, we can obtain equation 21. Okay, this is the vacuum contribution of the neutron vector meson that will appear here in the next steps at finite magnetic field. Here, for polarization, for the spin polarization plus and minus 1 that are the same polarization functions, we can obtain equation 22. But as I have said before, we have to regularize this function because it is ultraviolet divergent. So if you look to this phi function, we can expand this phi function in Taylor series in order to obtain the divergent contribution. That is this red term in equation 23. Okay, we can eliminate this term in equation 22 in order to regularize this phi function. So we can obtain equation 25. We can put this equation 25 and 24 in order to obtain a regularized polarization function. But we also, as we have removed, we have to put the same divergent contribution, but now this is regulated by the vacuum cutoff that we are using with the Pauli-Vilas regularization. So we can obtain equation 26, and the first term is the vacuum contribution that is in equation 27, and it's very easily to demonstrate that is exactly the same contribution that we have seen before for the vacuum result, okay? If we look to the polarization, spin polarization 0, we have a more simple result. We have just to do a Taylor expansion of this hyperbolic functions in order to see where is the divergent contribution. We can eliminate this contribution in equation 28, and also doing the same procedure we have seen before, we can obtain a full regularized polarization function for the spin polarization 0. Okay, so we can use these results in that conditions for the vector meson mass, and now we have just to set the parameters of this theory. These main parameters are chosen in order to obtain the vacuum value of the quark condensate, the pion decay constant, and the pion mass in the vacuum. Okay, and we also set the whole meson mass in the vacuum using that value of the vector Copley constant. We also have the set of Pauli-Vilas coefficients here. Before we go to our results, it's interesting to see what we have before. In 2015, we have this set of results with non-MFI regularization. Okay, in this procedure, we have some form factor function regularizing the equations for the effective meson masses and the whole mesons with the different spin polarizations. We can see here in the left the effective quark masses, depending on the summation of Landau levels. This kind of thing does not happen in our equations. Okay, and we can see also in both plots some oscillations in the results of effective quark masses and meson masses. There are other issues, but we will see later these other quantities that is interesting to us. For our results, we can see that we have the effective quark mass on the left, basically saying that we have the magnetic catalysis predicted by LATSI, and we also have in the right the neutral hole mesons with different spin polarization and also an unpolarized case, which is just the average value of different spin polarization hole meson masses, okay? The main idea here is the spin polarization 1 mass has an enhancement of the mass as function of the magnetic field, and we have a non-monotonic behavior when we look to the spin polarization 0, okay? If we compare a little bit with LATSI, we can see in the left the neutral hole meson with spin polarization 0, spin projection 0, sorry. I think I am saying polarization, but it's a projection. And spin projection 0, okay. We have a disagreement between the model results and the available data for the spin projection 0. And we think that the main cause may be the mixing between hole mesons and pions due to the magnetic field, and maybe the LATSI techniques that they use to evaluate these masses that are a little bit problematic to evaluate in LATSI. Maybe the LATSI guys from here can say a little bit about in the coffee break or in the next talk, I don't know. And we also have here in the right the comparison between our results and the model results with the two different LATSI groups, and we see a very good agreement between the predictions quantitatively and qualitatively for spin projection 1, okay? We can look to this meson masses and compare a little bit with all the results of NGL model with non-MFI procedures. Here, besides the oscillations we have seen before, we also have a very strong strengthening of these neutral hole mesons as function of the magnetic field in the right. And as we have in our work a very good agreement between our results and the LATSI, we think that magnetic field independent regularization can clear the path to a better discussion about the physics of this problem, okay? So it's not just a point about avoiding oscillations, it's avoiding oscillation, but also a better prediction of physical quantities. For this last plot, we have here the parameter space of this whole problem, okay? This neutral hole meson mass depends strongly on the choice of the vector coupling constant. So in the left, we have here different values of coupling constants. We have in orange the 2 times the effective quark masses, and we can see that not every value of vector coupling constant gives us a stable particle solution. So we have to choose very carefully these values in order to have full solutions. And we can see also that in the right here, the proportionality factor varying with the magnetic field. This is just a generic name, a critical magnetic field that is that magnetic field when the particle can behave as a resonance, okay? So this proportionality factor, in fact, have 2 regions in this diagram of stable particle solutions and resonance 1. So we have to choose this quantity very carefully, okay? So the main idea of this talk is we have to work with a regularization that can, in principle, avoid non-physical oscillations, okay? And the method is the magnetic field independent regularization. We can have these oscillations and non-physical results also at finite temperature, finite chemical potential, and so on. And for this purpose, we can use another method that we have proposed in 2021, that is the vacuum magnetic regularization, okay, which is based in the MFI procedure. And we can study the properties of the QCD phase diagram. We can study the thermodynamics, and I think Professor Farias will talk about. And we can also use the magnetic field independent regularization to clear the discussion about the physical quantities. And I can recommend this reference here when you can see a little bit more about these issues. And one example is the charged whole meson condensation, and the question if this effect really happens in this model. There are several other possibilities to explore for the future. We can use these methods to extend to finite temperature, so we can look to the vector mesons at finite magnetic field, temperature, chemical potentials, and also we can extend these models beyond mean field approximation in order to have better conclusions about the QCD phase diagram with strong magnetic fields. So this is all I want to say. Thank you for your attention.
So when you say the oscillations are non-physical, what's the main justification? Because couldn't they correspond to some sort of physical phenomena?
First, these oscillations, as we can see here, does not happen in lattice QCD. We can start to thinking in these points. We do not see these oscillations in lattice, okay? And this is the first point. The second point here is that, for example, in the top we have using as an example, the Fermi-Dirac regularization, and in the bottom, the Lorentzian one. So they change abruptly the results of the quark condensate, for example. I didn't show here, but we have these results also in meson masses. I showed the neutral hole meson mass, but we can see this for pions too, okay? So with finite magnetic field, with finite temperature and densities, we can see also some of these issues. So I think we see in some other talks in this workshop, but it is this point. This is the point. We have these non-physical oscillations because basically we are entangled magnetic field and vacuum contribution in some quantities that we do not need to work.
All right, I see. Thanks.
And what are the two curves in your plots? You have traced curve and full line.
Sorry?
You have two lines.
Yes.
A traced one and a...
Okay, different values of the chiral condensate in the vacuum.
Thank you, William. Can you go back to page 23? I think that's where yes. So you see the left-hand plot. Lattice data go down, and your calculation goes up as a function of the magnetic field. And you sort of hinted that there may be some problems with lattice way of computing taking the limit to the continuum, I guess. But the same behavior shows in the neutral pion channel. In other words, there is also a decreasing function as a function of magnetic field. So some works, people here in the audience have worked on that, particularly Norberto. They've shown that if you put a coupling constant that depends on the magnetic field, then you can go close to the data. Now, can you comment on this? Because see, if you do that, then you will spoil your spin one channel, I guess.
Okay.
They have to be entangled somehow.
I understand. Okay. This is a very interesting point. We have worked a little bit, in fact, a lot with the coupling constant, but we have not find any evidence that we can cure this behavior, but it's a little bit tricky to work with this coupling that magnetic field dependent coupling, because we have some difficulties in order to parameterize the theory. So maybe it's the solution, but I don't know. I think that Norberto's work can clear this point. I think he have worked with this coupling constant. So maybe he can say a little bit.
Yeah, I will propose to postpone this discussion to the end of my talk. Anyway,
Okay.
I would like to ask Enrodi to comment on the lattice calculations, please. Because this is not yours, and you have also done.
Yeah, I'm not sure which reference this is, but I can tell you a little bit about what is complicated on the lattice with these kind of hadrons. This is a neutral roll meson, so you have to combine up and down quark contributions in a non-trivial way. So U bar U minus D bar D, or something like that, and that gives rise to additional diagrams that is usually not calculated on the lattice. So I'm pretty sure that in this case these diagrams are missing, and I'm wondering, how are you actually doing it? So are you taking into account all connected and disconnected Wick diagrams coming from such linear combinations?
What we can do is just to, as we can see here, is to include this infinite series of quark-anti-quark polarization functions. So I think we do not include these contributions.
I think the author of this lattice calculation is by Andrei Chichov, I think. You know him? So I don't know exactly, but you have also done this calculation, no?
Yeah, we did.
And I think
I
you
just don't know by
don't get
heart.
the degrees.
I just don't know by heart what we got for the neutral row meson's spin zero component. I don't remember by heart.
Okay, we'll have to check that.
but
But I
let's
think
check that, yes.
your result doesn't get down.
I don't know by heart.
We have to check. Yeah, good.
More questions?
Maybe a very naive one. If you have a magnetic field, can you have mixings between pions and rho mesons or not?
Yes, basically due to the magnetic field, right? Yeah. Yes, I am not able to say the details because it's the work of Skokla in the next talk. So he can ask. Yes.
Okay, so let's thank William again.